All right, everyone, we're going to get started here today. Thank you for showing up on this last day for our last plenary. My name is Christina Taylor, and it is my great pleasure to introduce our speaker for today, Anne Almgren. Anne is a personal friend of mine. I met her about a year ago in Sweden, and she has a very distinguished career in numerical methods for PDEs, which we're going to enjoy in her talk today. So just to highlight some of her achievements in her career, she is currently a senior scientist at the Center for Computational Sciences and Engineering at Lawrence Berkeley National Lab. She is also head of the Applied Mathematics Department in the Applied Math and Computational Research Division. She's deputy director of the Xscale Computing Project's AMR-X Co-Design Center and was the recipient of the 2023 Lawrence Berkeley National Lab Director's Award for Exceptional Scientific Achievement. She is also a SCIAM Fellow and is a member of the editorial boards of a number of journals, including Communications in Applied Mathematics and Computational Sciences, the International Journal of HPC Applications, and Philosophical Transactions of the Royal Society A. Today, she's going to be sharing with us some of her work in, of course, adaptive mesh refinement, as well as multiphysics, algorithms, and HPC. So with that, I'd like to introduce Dr. Anne Almgren and have her take it away. Thank you.
So let me echo Christina's thank you. It's the last day of the conference. Actually, when I accepted the Thursday slot, I thought the conference lasted until Friday. Didn't realize. So anyway, and I have to say also, I'm not a social media person, but on this app, when it tells you, oh, 5 more people are coming to your talk, it gets really exciting. So thank you all to everybody who clicked that they were coming. I really appreciate it. It gave me hope that there would be an audience. And to those of you who don't click, just remember that it can be addictive. So I've been doing AMR for a really long time. I'm going to see if this. And in the beginning, I gave very generic AMR talks. I've decided that I like to branch out a little bit. So there's an author, Haruki Murakami, who has a book called What I Talk About When I Talk About Running. So an alternate title for this is What I Think About When I Think About AMR. And I would like to convince you that, another version of the title of this talk is This is Not Your Grandmother's AMR. AMR, in its blandest form, is a technique that you can use and you can apply it rote by rote. It's actually, to me, something more interesting. It's a vehicle for exploring algorithms and simulation. Hopefully by the end I can convince you of that. Okay, so the premise of this talk is that there are a lot of really interesting problems that we want to solve. I will confess I am in the simulation space, so there is no ML in this talk. I aspire to learn ML, but this is a simulation talk. So the problems we want to solve, and I'm talking about solving them through simulation, they are multi-scale, and I think we all accept that. And just as the ML people have the curse of dimensionality, we have the curse of the multis. So when we say multi-scale, we often also mean multi-rate, where we think of scale as being spatial, rate as being time. Also multi-physics, you also hear a multi-fidelity. So we have the curse of the multis. We need to solve really hard problems. This is probably the last time I'll get to use this slide. I used to work in wind energy, but we don't talk about that anymore. So again, narrowing my scope, I'm going to talk about solving these as PDEs. Again, I have full respect for ML approaches, but I'm going to focus on PDEs. The way that I solve PDEs is on a mesh. So that's framing this problem. This is going to seem a little pedantic, but let me go through the process that we go through when we think about how to solve a problem. The first thing we do is we say, what's our model? And our model is our mathematical representation of the reality. Reality is complex, so we have to focus on defining a model with sufficient fidelity where it means it can capture the processes that we care about, right? We don't claim that we're capturing everything, so we need a model. That's usually our starting point, a model with enough fidelity. Now, we want to solve this model on computers, so we need a method. And a lot of us spend a lot of time designing methods. It has to have enough accuracy. And we also, by the way, have to have a good implementation of that method, so the software is really important. In fact, I put software in the title this time. The other thing we need is we need resolution. And a lot of times when we think about this, we say, okay, well, once I've got my method, I'm just going to put it on the computer and run it big enough. Well, that's sort of easier said than done. We talk about, oh, I have a second-order accurate method. Well, that's great if you're in the asymptotic regime. What does it mean if you're not? Right? So we need enough resolution to get ourselves in the regime that the errors are acceptable relative to the answer that we want to get. Okay, so we've designed, we had a model, we had a method, we have some software. This is the real world. We have to run it on a real computer. We have allocations. So we have to care about time to solution because we have to care about whether we can get the answers, I say, before we forget what the problem is. For those of you who are young, as you get older, this is more and more of an issue. So we need low time to solution, and oh, by the way, it has to fit on the computer. This is also an issue. So we want to run it fast, or fast enough. We need it to fit, because some nodes are bigger than others, and we also have to be able to afford the kind of computer that we can run it on. And that maybe you have access to a supercomputer, but maybe you don't. Maybe you have a cluster, maybe you have a desktop. You are trying to do the most science possible with your resources. So better or worse, we live in a world of constrained resources. That means that in finding a solution to this issue, there are going to be trade-offs. So if computers were infinitely fast, we had infinite allocations, they were infinitely big, we would not do AMR. Right? Sometimes people say, oh, what does AMR get me? Well, it doesn't get you a better answer than a uniform fine grid or a uniform small time step. It just allows you to get that answer in the world of constrained resources. So if we had those unlimited resources, I would not be talking about AMR. AMR, adaptive mesh refinement, in its traditional sense, and I'm hoping to convince you by the end of the talk that there's more to it than this, is all about getting faster time to solution, being able to fit on the computer, and it might be that you want to solve a bigger problem, and it might be that you want to solve your known problem faster. Okay? Or maybe you want to add more physics. Somehow you want your problem bigger in some way. It could be in number of mesh points, it could be in how many processes you include. Again, given constrained resources. The trade-off is complexity. Okay? There's always a trade-off, right? There is really no free lunch in this business. So you can get those things, but you have to think harder. And you have to think harder about your algorithms, and then you have to have the software to support what you came up with as you were thinking about that harder. Okay, I started by saying, oh, there are all these interesting multi-scale problems. How does what I've just said connect to the multi-scale? And I've had people say, okay, I'm doing this problem, homogeneous turbulence, but AMR is going to make it all better, right? Well, no, it actually doesn't help. There's a premise in AMR that there are different regions, and it's regions in space in our case. There are different regions where the resolution requirements are different. And it could be because there are static features in the flow. If I tend to talk in terms of fluid dynamics, it could be there are static features. Maybe it's flow over mountains, maybe there's an obstacle, maybe something interesting is going on there. So it could be a static feature or it could be a dynamic feature. But a premise is that there are different regions, therefore we want to be able to do different things in different places. And this is just a classic example I use. So I think a lot about scales, and if you want to capture something like the weather over the US, you need a big enough grid that you're going to get flow. You still need boundary conditions, right? You need boundary conditions, you need some larger scale thing here, but you need to be able to capture all of this. I tried to move this from Florida to Chicago, and my PowerPoint skills are not that good, so I apologize for that. Let's say you want to zoom in. You need fine enough scales to be able to resolve whatever the feature is where you are. Again, in our world, the problem is you can't do uniform, right? This would be the answer. In our unlimited resources case, you can't do it. So this is an answer, right? This is mesh refinement in the sense of block-structured mesh refinement, okay? We're going to talk about other types, but for the rest of this talk, I'm basically going to be focusing on what we call block-structured. As you can see, it is it's a structured grid nested within another structured grid. Okay. Is that your only way? And obviously not. And I think a lot of people here use unstructured grids. They use all sorts of finite. There's large number of methods. The things I talk about are primarily in the context of finite volume unstructured grids. It extends beyond that, but for the purposes of what I say, that's mostly what I'm talking about. So just to, again, set the scene, is block structured refinement the only answer? And the answer is, of course not. So unstructured grids, I'm not an unstructured grid person, but I want to give them their due. When I look at, I love this picture, I'd forgotten where I got it. I love that picture because I do not know how to cover that surface with a structured grid. I would not even try, right? Absolutely triangles, not squares in some sense. So unstructured grids, you can fit them to any geometry. Now, when I first started doing this and people talked about mesh generation, I said, well, what's hard about mesh generation? I mean, you take a piece of graph paper and right? That's your mesh. And then I realized, oh, this is mesh generation. So structured grid, we get to dodge this, but unstructured, once you've made your mesh, it's very powerful. Unstructured mesh, you have to worry about bookkeeping, right? So in in structured grid, if I have a point, I have a variable, and I want to know the I plus 1 value, well, I know it's to the right of the I value. In unstructured, I have to maintain this. I have to somehow keep track of the connectivity. So again, very doable. Lots of people do it, but it's a complication. So geometry generation is time-consuming. The connectivity can be expensive, but it gives you a lot of flexibility. And there are a lot of great things about it. I'm not trying to diss it anyway. Powerful, not necessarily cheap. Again, zooming in on structured, why do I like working with structured meshes? So one is discretizations. It is a very easy way to write discretizations. I think most numerical, well, I actually haven't taken a numerical analysis course in a long time, so I don't know what they do. But a natural thing to do would be to say, how do I define a derivative? Well, if it's an x derivative, I take the value on the right minus the value on the left. That fits very naturally into a structured grid paradigm. So it's easy to write discretizations. It is something that we think about a lot on, well, actually on CPUs and GPUs, is the data access patterns. So it is much easier to lay out your data in a way that the values you want to use are contiguous. So you can be contiguous in I or J or K, depending on how you want to do things, but you can control your data access patterns more easily. So it can get you some efficiencies that you would have to work a lot harder for in other ways. Say that. Obviously, the mesh generation is easy. It looks like a piece of graph paper. If we want to do boundaries, that's always the question. There are ways of doing, we happen to do a cut cell approach. It is a way of generating or of representing geometry in a fluid flow, for example. It is not, there are issues with that. I'm not going to say it's perfect, but if one wants to do complex geometry, one can. Okay, takeaway, structured meshes to me sound very appealing. But how do you get this variable resolution that we saw we need? Just a disclaimer here, I talk about graph paper, that's how I think of structured meshes. There are ways to get variable resolution with structured meshes, and these are just some examples of them. So again, you can deform your mesh, you can bring the grid lines in. So when people talk about mesh refinement, sometimes in particular they mean that one on the bottom left, where you have the same number of grid lines and you adjust them. What I'm going to talk about is more general than that from my speaking, and maintains this local regularity that we like. Okay, so what I would claim is in the structured world, block structured mesh refinement is sort of the best of both worlds, right? And if you think about that picture of the US with Florida refined, so I have higher resolution in the regions of interest, and I, as the user of a software code or designer, get to say where my region of interest is, right? I have local regularity, which for all those reasons that I like structured mesh, I now have that locally. So if I want to write a derivative, it's a straightforward discretization. I have all these advantages of data access, but it's kind of a patch-based thing as opposed to being regular across the whole domain. One of the really nice things about it, which it's not obvious until you start to do it how nice it is that you start to think, so domain decomposition has been around. Domain decomposition does not imply this multiple level, but in some sense, AMR is a way of doing domain decomposition. We just don't require that the meshes fill the domain, whatever your computational domain is. And it gives you this very nice hierarchy where you can do, so we typically do MPI plus X. So now everything is in terms of patches. We don't say, oh, I have one box that covers my domain. We say we have patches. And again, domain decomposition is the same idea. I can distribute patches to MPI ranks. So that's the course level. On that MPI rank, I may have multiple boxes. Let's say I have one box there. It's a structured box. Now I can do my fine-grained parallelism, and I can do that with OpenMP, or I can ship it all off to a GPU, whatever form I want to use there. So it makes MPI plus X this very natural way of doing things. MPI across boxes, and then X, CUDA, OpenMP, whatever, across cells. So it's a really nice feature that you don't realize until you quite get into it. So that's the hierarchical parallelism. The trade-off that I talked about, this complexity, that comes at the boundaries, at what we call the coarse-fine boundaries. So what's interesting about this to me is there's a certain machinery for the problems that we've already solved, and I'm going to show you just a little bit of that. But what I tell people when they say, okay, I have this code, I have a single grid code, I want to make it adaptive, I want to use AMR. And the first thing I say is, what is true at the boundaries? What property is true of your solution, or what needs to be true, Some algorithms, it's conservation. Some algorithms, we can talk about some other things. But that's something that you have to know if you know your physics and you know your algorithm. So that's the special discretization. You do something special, but that's code dimension 1, right? If you're doing a 3D problem, it's 2D planes. If you're doing a 2D problem, it's 1D lines. So you're doing that extra work only at these very special places. If you have like a feature with strong gradients, and that is safely inside your nested region, then your strong gradients are not at the same place as your coarse-fine interface, and everything kind of works well. We do in practice try to put the interfaces where things are smooth. And again, relative to unstructured grids, I have very little bookkeeping because each patch is structured. Again, these are two examples. The one on the left is some kind of swimmer that I'm not sure I want to know what it is. It's got about 4 levels of refinement there. The other one is a simulation from a project I worked on with, again, that's a turbine blade nested in a larger flow. Okay, let's see that. Okay, I don't know how to click that movie to make it go. So the A in AMR is adaptive. Again, I talked about static features and dynamic features. I apologize. The upper left is 2D, the lower right is 3D, and is there a way to click to make the movie go? Maybe not. Okay, that's going to be a problem. Can he do it? Can you make the movie go? This is going to come up. Okay, so just the idea that, so the A in AMR is the idea that we reevaluate where the region of interest is, and we talk about it as moving the boxes. We don't actually move the boxes. What we do is we destroy and create without losing the fine grid information. Okay, so again, AMR is great. Look at all this resolution I get sort of for free. Well, there's the complexity. What are the type of things that I have to think about? And I told you one of them, which was number 3 there, which is how do we sync across levels? And that's going to come down to what has to be true. But the first one we have to say, that there's sort of 2 flavors, and we actually have arguments in the community about how we label them, because block-structured AMR, what that's telling you is that the region that is refined makes a rectangle. There's also something called cell-based AMR, which in the pre-GPU days was more popular. It's nice because you don't waste refinement, but it adds a lot of complexity and it actually costs you computational time. So in the spirit of block structure, we're going to talk about that. I'm talking about solving PDEs. The partial part means I've got something besides my spatial direction. I've got a time. What do I do in time? And there are a lot, it's interesting. So AMR started off in a very particular setting. There are a lot of folks who think that that defines AMR, and I'm hoping that one of the things you take away from this is that AMR is a much more general tool. So when we say, do we advance all levels with the same time step? Maybe yes, maybe no, right? It's not a given. How do we sync the solution? We're going to talk more about that. And also, how do I decide where to refine? In most cases, it's fairly straightforward. There are a couple cases where it's not, and that's an interesting question. There's some other things. So it turns out that with mesh refinement, I'm talking about mesh data, but you can add particles, you can add boundaries. There are all sorts of interesting load balancing strategies. There are a lot of things to think about, but we're going to focus on the ones that are not, that are bolded here. Okay, so in terms of defining the strategy, like I said, we used to fight over who gets to call theirs block structured. So what we said now is their block structured comes in 2 flavors. The left is what we call level-based. The right is what we call octree or quad tree. The idea here is, and on the right was, okay, they've come out of separate camps in some sense. So on the left is, if you go back to Marcia Berger's work in the 1980s, it was called then patch-based AMR, but then the folks on the right got mad that we took the word patch-based, and so they said, we're patch-based too. So on the left, what you can see is, 1, the grids do not have to be the same size. So what you see here is black grids are coarser, then blue grids, then red grids. So 1 is they're not all the same size. They're not 32 squared there. And 2 is that it's not a tree structure in that one of the red grids has 2 parent grids, okay? If you contrast that to the right, where you have a tree structure, every what we'll call child grid has a unique parent. So there are efficiencies that you can get on the right because when you're looking to fill your boundary conditions, you know exactly where to go. The flip side is on the right, if you have a coarse patch and you say, that point there, I need to refine that region, you have to refine the whole thing. Because basically you're either a leaf node or you're not. You can't be a coarse grid where part of your grid is refined and part of it's not. You're either a leaf node or you're not. So there are trade-offs, and there's great work in both camps and there's great software in both camps. The one I'm going to talk about is on the left. One of the reasons that we really like it is when we think about algorithms, when we're first designing algorithms, we tend to think, so the first thing we do is we say, what do I do on a box? A single box, maybe I have boundary conditions, how to advance my solution there? And then our next version of sophistication is we kind of say, how do we do this on a collection of boxes? Now that's domain decomposition, right? So I can't assume that the edge of any box is necessarily at the domain boundary. A lot of algorithms we think about in terms of levels, where a level means I'm at a particular refinement. And the way we decompose on the left is it fits with that way of thinking, that I have these two red grids. Now those red grids aren't touching, so I'm going to solve separately, but the two blue grids, those are touching, and at that fine interface, they don't know it's a different box, okay? On the right, you tend to think of things in terms of just individual patches, and if you have a coarse grid like this and you have a fine patch here and a fine patch here, they don't necessarily, in the way of thinking about the octree, they don't necessarily know they're on the same level. I mean, they know what their dx is, but there is not a natural way for them to talk to each other. So it's really, it's kind of a design philosophy. They both work. But anyway, I'm going to talk about the left. All right, this issue of subcycling. So again, it used to be that AMR, in the traditional block structured AMR that came out of the Marcia-Berger work, AMR meant subcycling in time. Okay, so to be clear what subcycling means that as you refine in space, you also refine in time. That makes sense for a lot of algorithms. It is a natural thing to do, okay? So when you subcycle, you take one step on the coarse grid, and then let's say you refine by a factor of 2, then you would have to take 2 steps on the fine grid. What we'll see in a minute is what that does is that keeps the ratio of your time step to your spatial step constant. That can be a good thing. It also introduces complexity because you're now asking for boundary conditions from the coarse grid at an intermediate time where it doesn't necessarily have a solution. Okay? Well, there are efficiencies in that. The flip side, if you run everything at the same time step, let's say you have multiple processes. You have advection, then diffusion, then reaction. You can do your advection across all your levels, and everything will be synced up with your advection, all your fluxes will match, everything's great, before you go on to your next physical process. So you can either decompose your problem in some sense by saying, I want to do everything at a single resolution before I go on to the next resolution, or you can say, I want to do everything advection related before I go on to diffusion. So it's really just 2 different ways of slicing your problem. There's not a single right answer to it. Again, this is a question to which the answer is context matters. And again, this is one of the classic, this is flow hitting a ramp. The ramp is represented by EB. That's a classic AMR problem because you don't need resolution anywhere until this hits the ramp. Okay, the subcycling again, on the left I have level 0, level 1, level 2 is resolution. I'm moving forward in time. That's just a graphic of what subcycling means. Again, the reason that subcycling was so important in the beginning is the algorithms that were used were designed to work where the ratio of dt to dx was, let's say, well, there's a speed in there, but you wanted to keep, there was an optimal ratio of dt to dx. What that meant is if you did not subcycle, then you had to use the dt of the smallest, the finest grid. That meant that when you advanced your solution on the other grids, you were using something that was not in the space where your algorithm performed best. And that little graphic there is if I do scalar advection with this particular scheme, what I see is, sometimes we think, oh, smaller time step, better answer, right? That's what it means to converge in time. So smaller dt should always give me a better answer. No, smaller dt gives me a worse answer in some schemes because it's about the balance between dt and dx. Okay, and it's subtleties like this. So for that scheme, you absolutely want to subcycle in time. Other schemes, that's just not the case. The other case where it gets interesting is sometimes you have a problem where you actually can't solve it on the coarse grid because it's too unresolved. So in that case, you can't advance the full coarse grid before you do the fine grid because you just can't get a solution there. We want to be able to access those types of problems, so we say, okay, in those problems, you're going to accept that you can't solve it on the coarse grid, you're going to solve it on the fine grid, and then you'll average down or whatever you need to do. So that's one case where you want to, might want to not subcycle. It's also the case that when you do octree, so the octree folks always used to not subcycle. They have subcycling versions now, but if your paradigm, especially in your software, is that you just loop over all the leaves in a tree, all the leaves in a tree, those leaves are at different resolutions, so if you're looping over all of them together, you'd better be giving them the same DT. They've gotten around that, but it's a complexity. Just to be clear, there are much fancier ways of doing this. You can do things where, there are actually some really exciting ways where if you want to take a time step, you have multiple spatial resolutions, and then you can do sort of iterative things, and you can imagine, this occurs in a lot of different settings, but you can do a sort of a lower order, bigger time step coarser grid advance, and then you can do a finer mesh, finer time step for a correction to that. There's some spectral deferred corrections types of algorithms. There are a lot of interesting ways to mix the time stepping and the spatial resolution. Okay, and then the other thing is that you often want to do the fastest thing, and you would think that subcycling is always the fastest because you do the fewest number of total advances. It turns out that sometimes that can backfire because of additional work. Load balancing can completely change your metrics. So the minute you get into the details, it actually gets more complicated. Okay, question, I think it was number 3, what does it mean to sync across levels? I'm not going to go into this in huge detail, but the idea, and again, I apologize for this graphic. I grabbed this from an old talk. Space is horizontal, time is vertical. So I have find on the left, course on the right. I want to advance something, and I have ut plus fx, where f is a flux. Okay. The idea is when I advance the course grid, I have to see course information everywhere. The red is filled in data from the course grid that's under the find. Maybe I've averaged down there. When I want to advance the find grid, I have to fill some ghost cells. Those are the red on the right. In each case, I am computing a flux at the location of that course find interface. But I'm doing it separately on the course grid and on the find grid. And here we're doing the same DT. So we advance the course grid, we advance the find grid, and we say, am I happy? Am I done? And if you look at what you've done, so first you might say, well, I want to keep them sort of in sync. So the thing we often do is we do average down. So we make the course grid that's under the find grid, we make that be the average, okay? But then if you think about it, let's say you have a conservative scheme. A scheme we know a scheme is conservative if the way that we advance the solution is we compute a flux at every face, a unique flux, and we use that to advance the cell on the left and the cell on the right. Well, here I've computed 2 different fluxes. So how do I fix this? And the answer is I have to make the fluxes consistent. We have a premise in this that the find grid answer is better than the course grid answer, because if we didn't, then why would we be refining? So what we do is say, I've done one time step, I used the wrong flux, shame on me. So now what I'm going to do is I don't have to go back and recompute the flux because I know how the flux was used to update the course solution. So it's actually very simple. I update that one course cell that's next to the course find boundary so that it gives me the answer that I would have gotten had I used the find grid flux. How easy is that, right? So this is what is traditionally called refluxing, and it seems just trivially simple. It's wonderful. And in this picture, this is now a 2D picture where both of those are spatial dimensions. You're effectively replacing the big red arrow by the average of the 2 small red arrows. You're conservative. Okay. It's really easy. Now, complexity, what we do is we integrate course levels, we interpolate boundary conditions, we integrate find levels, then we do our synchronizations, we average, we reflux, right? That's easy. Okay. Okay, now let's go to the Navier-Stokes. So Navier-Stokes, I've got a diffusion term in there, and I apologize, I know there are a lot of solids folks, so I tend to think in terms of fluids. To solve the divergence constraint, I need to solve some sort of elliptic equation. Okay, let's talk about elliptic equations. Again, I apologize for the notations grabbed from an old slide. So if I were to solve the elliptic equation explicitly, where I computed a flux and then used that flux, I would do the same thing. But typically, we solve elliptic equations we solve them implicitly. So I'm doing some sort of solve, and it turns out that there are 2 things I need, right? It's a second order equation, so I need 2 things. I need the values to sort of match to be consistent, and I need the fluxes. I need the gradients to do the right thing. So if I'm solving Laplacian equals 0, that should be a straight line in 1D. If it's not, then I haven't solved my problem. And cutting to the chase, because we're low on time, if you solve an elliptic equation implicitly, then you must correct your equation with the same type of solve. So the takeaway is, in the case I showed you, all you got to do is update the value on the coarse grid next to the fine grid and move on. If I've solved an elliptic equation, I have to do an elliptic solve for the correction. That means I'm doing a solve over the whole grid again. Now, I can get away with doing it at the coarse level. There are ways to make this faster, but the whole idea is the way that you correct the mismatch depends on the operation. It's not always local. It's not always as simple as just adding a value. It's elliptic. Parabolic has a similar thing. Back in 1998, so before this paper, AMR meant AMR for compressible flow. Everything was an explicit operation, and it was compressible. Then we said, oh, let's do it for incompressible flow. How hard can that be? So it turns out the only way we could think of to explain the algorithm in the paper was to say, these are the mismatches. Here are the mismatches, and here's how we fix them. And as you can imagine, well, you've done advection and then diffusion, but then I'm going to go back and correct the advection. And so the correction to the advection has to be seen in the diffusion, and then you have to correct the diffusion. And so the correction to the advection has to get absorbed into the correction for the diffusion, and then the correction for the advection and the diffusion has to get incorporated in the correction to the projection. Yeah. So anyway, it works. We'll leave it at that. Okay. So the last thing about refining and de-refining. 90-some% of the cases, it is really obvious where you want mesh refinement. We don't think too hard about it. When you're doing generic fluids, let's say, vorticity is usually the answer. That's where the interesting gradients are. If you're doing something, you're doing combustion, it's usually where the reactions are, right? This was a kind of it's something I was working on recently with some colleagues up at Pacific Northwest National Lab. Really, really, really simple 1D case. So there's something called this club model that has to do with turbulence and microphysics, and you kind of want to figure out where the cloud is, and you want to get some quantities right. And so you solve it on the coarse grid, and what you see here on the left are the 4 different grids we did. There's a uniform fine grid, we'll call that truth. There's a uniform coarse grid, which is what they actually do, and then there were 2 different experiments. In this case, we weren't doing the block structure per se, we were actually just sort of moving lines closer. And what you see is the red, I won't even call it a curve, the red line is the coarse solution, and the other lines are basically the fine solution that you get if you refine in the right place. The point of this one is the coarse solution and the fine solution aren't even in the same place. Now, in this case, you would actually probably refine the whole region, you'd be fine. The takeaway, though, is that sometimes you don't know in the coarse solution where you need the refinement. Where is that gradient really going to appear if I really had the resolution? So it's an interesting. Sometimes you can work it out. If you understand your problem, you understand the physical processes, you can say, I know what will lead to that gradient, and therefore I know I can put refinement there. It turns out in cosmology, I've got to talk faster. In cosmology, it turns out that putting gradient makes Gaussian form faster, and so you have to be really careful because by the act of putting refinement, by the act of adding refinement, you've triggered a process. So you have to be a little careful with how you use this, understanding that your answer will look different between coarse and fine. Maybe. Okay, I just love this movie. AMR is not just for fluids. This is an example. We do particle accelerators, so now we've got electric and magnetic fields. We've got a beam of particles there. This is what your particle accelerators are not supposed to do. It's all about beam stability. So this is just one of our examples. Okay, remember that really pedantic slide I said about first you make your model, and then you choose your method, and then, okay, that's the way we traditionally think of things. We can upend that, and a lot of people are thinking this way now. You say, wait a minute. Let me start by choosing my resolution. Once I've chosen my resolution, let me ask what's the right model for that resolution. So a really different way. Instead of saying, here's my equation set, I know this equation set is valid over all resolutions, let me solve it on as fine a grid as I can, I say, wait a minute. The model may depend on the resolution. So let me talk about the resolution. This can be a particle versus continuum representation of a fluid. It can be compressible versus incompressible and elastic. It can be different turbulence models at different scales. There are a lot of ways now we call this AMR, adaptive mesh and algorithm refinement. I can change what I do at each level. And this is, okay, let's see if that, there we go. So this is a really fun example we did where you would like to represent this. This is just basically random walks. It's random walkers if you think about the particles moving, they're going to do the right thing and give you the right answer as long as there are enough of them. The continuum representation is great. It's much faster because it's sort of some composite value. So what we're doing here, let's see if I can, try to play it one more time. Can I play it one more time? Maybe. There we go. So what we're doing here is we're using the AMR concept to say, I can solve using particles in one region, using a fluid or a continuum representation in another region. What's fun about this is I'm using all the AMR framework. I didn't actually, in this case, refine, right? So we start with this premise that it's all about mesh refinement. And then you realize, no, I can use it. I can refine the algorithm. It's not clear what it means to refine the mesh if I don't have a mesh, I have particles. Just to get the pictures going, this is a 3D example where we have potential wells. If you only did the continuum representation, you get the wrong answer, it turns out. So you need the particles to get the right answer, but they can also be too expensive. So we can use this concept of doing different things in different places. We can use all of this AMR machinery that we have to do that sort of thing. You have to change what you mean by these operations. What does average down mean if it's particles and fluid? How do you interpolate ghost cells from a fluid to particles? Refluxing, what does it mean to reflux between particles? So these are the questions that you have to understand your physics, but you've got the machinery to do something really powerful. Again, the point is AMR itself is machinery. It's what you do with it that's really interesting. Okay. And then just, again, I've talked about this machinery. I have to give a short plug. So we actually have an AMR framework. It's called AMRX. If anybody's interested or tempted to try it, there is support for all of this in software. It has mesh data. It has particle data. Works on supercomputers. So in the exascale computing program, we were a co-design center. And so we came a long way, and this works on all the big machines, et cetera. This is more at a glance. This is just a sampling of codes. The picture of the US there is an epidemiology code, right? It's an agent-based model just using the particles. Actually, you can use the mesh to supply data about whether something in a region, the particles can talk to the mesh. Similar things in a lot of places, but just a lot of different applications. Brandon Reynolds at Iowa State is doing a lot of really neat solid mechanics applications. So that's been a lot of fun. And again, we're part of a larger ecosystem. Thank you. And again, I just want to thank all of you for lasting till this last day. Okay.
All right, so we are right at 9:10, so we have about 5 minutes for questions. And I believe there is
There's a mic somewhere, but I don't know.
there is a mic somewhere, we believe. We're not quite sure. Yes.
Oh.
So maybe
Wait,
while you are thinking of
Does she have a
questions,
mic or
or
question?
we have a question. Okay. Yes.
Hello, thank you for the talk. Can you comment a bit on refluxing when you have non-conservative terms in your system? Refluxing on non-conservative terms.
Right. So the question is, what do you do if you have non-conservative terms? And the answer is, what needs to be true about your equations? So sometimes we can write things in a non-conservative form. There might be a conservative form that is equivalent that sometimes we don't write. So for example, in incompressible flow, you can write things as a divergence or you can write it as an advective term. That's one example. So comment one is you have to ask yourself, is there some underlying conservation that you need to maintain? If there isn't, then you might not need to do anything if you didn't use necessarily information that crossed the boundary. So for example, if you have what we call body forces, so maybe gravity's acting here and gravity's acting here, they're on different sides of the coarse-fine interface, but the fact that there's an interface there doesn't affect the body source, you don't have to do anything. So it's really a matter of understanding how the terms are contributing. Does that make sense?
Yes.
Okay.
Yes, thank you.
Oh, there's...
Thanks very much for the talk. Do you have a sense of where you expect the hardware is going? If these hardware vendors keep focusing on deep learning, are those machines going to be good for these adaptive codes?
So I have no insider knowledge, I'll tell you that first of all, right? GPUs took over our world. Obviously, sort of AI/ML is taking over our world. In the space of solving physical problems, they still need training data. So you still need simulation codes to give training. I mean, they're database ones, right? But simulation data provides a lot of the data that we should be training a lot of them on. Now I won't speculate about the future. Other than the coming at limited resources will continue to apply, right? Computers are limited resources. We who want to solve problems have to do the most that we can with the limited resources. I'd like to think we could shape that trend, but yeah, that's all I'll say. Yeah.
That was a great talk. Thank you.
Thank you.
This might be a stupid question, but if you were considering like using Fourier transforms to represent some sort of a grid pattern, you need the uniform increments, and then you do remeshing and different scales. What is that? Any insight or tricks to that? Have you looked at that?
The answer is basically no. Basically no. I mean, so, for example, we don't know how to do a multi-level FFT. We can do FFTs on, so the patchness gets you a lot. The rectangular patches gets you a lot. And then you can say, can I couple, if you're trying to get into a solution as fast as possible and you're willing to accept a little bit of error, you can probably cobble things together. But no, we don't have any tricks for that. I wish we did. Oh, yeah.
Thanks again for your talk. Is there a concern with maybe like stiffening the matrix or kind of affecting linear solvers when using AMR, or is that not a thing?
So yeah, so just one comment is we don't think as much in terms of matrices, but we do a lot of linear solvers for different operators. The answer is yes, because you change okay, so there's two different things. You can solve, if you're doing the level solves where you solve everything at level 0 before you go to level 1, then each of, and let's say you have to do a linear solve as part of that. That solve only sees its level. So it isn't affected because it's a single resolution solve. If you do multi-level solves, the other thing I didn't really talk about is if you like multigrid, which I happen to like multigrid, AMR and multigrid play really well together because multigrid is all about levels, and you can do a single solve where if you have a V cycle, where your V cycle, you're still solving on the whole domain, but then above here you have AMR levels that are on subregions. So in that sense, if you're doing, for example, a multigrid type algorithm, again, every operation is a single level operation. So the AMR is almost like part of the multigrid. If you were to do a single, for example, direct solve across levels, then you start getting into issues of condition number if you do large refinement ratios. So you can get there. I would say it's not our biggest headache right now, but it's real, yeah.
Thank you.
Sure.
What drives the adaptation? Is it error indicator or the error estimator?
So the beautiful thing about it is it's you. Okay, so for example, in Flash they said, we're going to take the Laplacian of certain quantities. That's great if it's all about the gradient, right? So if you think about things like that, so a constant value you probably don't need to refine. If it's the value's linear or really smooth close to linear, you probably don't need to refine because your coarse grid representation will be as good as your fine grid. So the thought in codes like Flash was, the Laplacian is the answer because that picks up changes in gradient. That's where things can be sharp, right? Sharp changes. It turns out that's way too limited an answer because, and it's an interesting thing because, like I said, in cosmology there are cases where the refinement can actually trigger things to happen that wouldn't happen. It's also some case that and what they actually do is they run a coarse grid calculation. They say, where does the coalescence or the galaxy start to form? And then they run it again, and then they put the refinement there. Sometimes, for example, in combustion, you do it where there's chemical reactions. And you don't want to wait until the reactions happen. So you don't want to trigger, for example, on a heat release. What you want to trigger on is the presence of, maybe it's a catalyst, or the presence of the fuel plus the oxidizer. So it really, there's a way to use AMR as a black box, but I actually don't like that because I think it's much more interesting to say, what do I know about my problem, and how can I use that knowledge to do better? But you can do the Laplacian if you want to. And we also have things where you can refine. I could say, in this region, if the temperature is above this and not in this region, I mean, you can mix and match and do ands and ors. There's all sorts of things that you can do. Yeah. Oh, we're probably at time.
All right, so we are at time. Thank you, everyone, again for sticking it out. Let's thank our speaker again.